Hello, my name's Jacob, and on behalf of encoord, welcome back to the Intro to Saint video series. In this fourth video, we're going to cover a basic workflow in Saint. This video series does build on one another, so if you have not watched the first 3 videos, I highly suggest you watch those before watching this video. A really important step in most workflows of Saint is looking at results, and that motivates our final property type. So far we've talked about network properties, event properties, and now we introduce result properties. There are 2 types of results properties. Base results, which are properties that are solved for directly during an execution, and derived results. And these are common results that come from base result combinations or arithmetic. Why does this matter? Saint saves all base results by default to those solution files. And any result, base result or derived, can be retrieved from a Saint solution at any time. For a concrete example, let's pull up the documentation. If we go to Objects, Electric Objects, and then we find the electric demand EDEM objects, we can see the different property types that we've talked about so far. For an example of base results versus derived results, let's look at the base results of an EDEM object. We can see for the DC UC OPF scenario, a base result of an EDEM object is P, the total active power. A derived result for an EDEM in a DC UC OPF case is PNS, power not served, which is the difference between the scheduled and delivered active power. Here you can see that PNS is a derived result because it's calculated as the sum of P set minus P. Now that we understand the mindset of Saint results, let's cover some of the mechanics of viewing them. A very common way to look at results is with charts. With the GUI open in the same place that we left it in the last video, let's open a chart. We can do that by going to View and Chart. I'm also going to minimize this mini-map just to get a better view. I can click on different objects to see their default chart. For example, let me look at the default electric network chart. Here, I can see a stacked generator dispatch plot for this scenario. I can also click on different objects in my map to see their default. Let's say I just wanted to see a plot of the shadow price for this node. I can right-click, Plot Window, Shadow Price, and I can see a chart of the shadow price at this node throughout the course of this scenario. Currently, I'm only looking at one time step on my map. Another way to look at results over time is with animation. So going back to the GUI, I can see that my map window is currently showing the results for a single time step, which happens to be midnight on July 16th of 2023. To animate these results, go up to the Simulation tab and click Play. Now in the chart, I can see a red line that shows the current time being displayed on the map. And I can see in the map, the time is changing on the bottom. This functionality can be really helpful for going backward and forward throughout different time steps and finding ones of interest. There's another way to view results which we haven't really covered yet, and that's the command window. I'm just going to do some tidying so we can see the command window. The command window uses IronPython syntax, and that's a Python-like interpreter that allows you to interact with the objects in Saint. You can use the command window for accessing object properties similar to how we were using the property editor before. It uses the convention objecttype.objectname.propertyname, and then you can put in many optional things like units after that. For example, let's say I want to get the current shadow price at the Albany node. To do that using the command window, I would type in that this is an electric node object, Eno. The name of the object is Albany, and we can see that it actually will autocomplete for us, so we can use tab to autofill. And the property that I want to get is the shadow price, which is P shadow. We can see that it's suggested there. When I click enter, I see that the current shadow price at the Albany node is 37.9125. An example of how I would get all the shadow prices for all the nodes at the current time step is by using the percent sign as a wildcard. That would look like, for eNode objects, for electric node objects, I want to grab all of the shadow price, P shadow, tab, enter. And I can see I'm presented with a list of all of the shadow prices at the current time step. Many other IronPython functions are available in the docs. Let's pull those up real quick. If I go to the Functions, Expressions, and Conditions page, I can see different pages on IronPython Basics, IronPython Plotting, IronPython Tables. These can be really helpful for doing advanced nuance analysis in Saint. To show a quick example, let's use the table function. And what I want to get is a table of all the shadow prices. So we've done that before. So shadow prices are the properties of an electric node object. So I'm going to say all of the electric nodes, and I'm going to grab the P shadow price. And what I want to do is grab it for all time, right? And so I'll say what I want to do. I want to grab it over all the time. The syntax is to use your wildcard operator surrounded by parentheses to get all of the time. After hitting enter, I can see my custom table of shadow prices at all the nodes over time. A fun trick in Saint is that any table you make can be exported by right-clicking this top corner, export to CSV. This can be really helpful for using the Saint graphical user interface with your existing planning processes. Let's show another helpful example. Let's use the plot command. For this example, I'll plot the total active demand of my network in gigawatts with a line width of 6 in the color of green. So the syntax of that is plot my electric network. What property do I want to get? Active power demand. In what unit do I want to get it? In gigawatts. And I want to make sure that I grab all of the time steps available. My line width, I said 6 for this example, and I want to do the color of green. I close, I hit enter, and I can see my plot of my total active demand throughout the course of this scenario in green. I do want to quickly mention, as you'll see this in the docs and on discussions on the user forum, you actually do not need to include that final percentage sign. So actually, if I go pull up that command by using the up arrow, I can delete that final percent sign. If you omit this final wildcard from the plot and table functions, Saint will use the chart window start and end times by default. Any commands that you put into the command window can also be saved into an IronPython script. To see the existing IronPython scripts of a dataset, you can go to the Project Explorer and you can look at the script files. In this case, some script files were included. Of specific interest to this scenario, there seems to be a script file that's for looking at the results of the PCM peak demand week scenario. Let's look at this script. Looking at this script, I can see that it contains an endplot function with some predefined colors and legend configurations. Let's run this. Looking at this plot, I can see that this IronPython script was for creating a detailed generation fleet dispatch plot where the thermal generation is broken down by fuel type. Now, let's step through this workflow. Please follow along if you would like. Let's mimic a fresh open of Saint. And let's even minimize this command window. The first thing we'll do in this workflow is open a network. Recall, we open a network by using the Network tab and selecting Open, Open Electric Network, and selecting our eNet file. Let's start by checking out some network properties. Recall, to look at network properties, we should use the property editor. We could access it either by clicking on the property editor that's been hidden here, or we can go View, Property. Let's use our Model Explorer to explore different objects in our network. For example, I see that there is a node in Albany. Let's view that on the map. Oh, it looks like this node represents the Riverside substation. Let's see what fuel generators are in this network. It looks like this network contains 10 fuel generators. Let's see where those are on the map. I'm going to shift click to select all of them, right click, and say Select in Map. I can quickly see that I have fuel generators located throughout this network. In more complex workflows, you might do more dataset interrogation to learn a little bit more about the layout of your network and what types of objects exist in it. But for this workflow, I'm going to look at my Dighton fuel generator. It looks like currently it's a 508 megawatt generator. Let me change that to be a 300 megawatt generator. Let's say it's being derated for whatever reason. I'm going to quickly deselect these objects by clicking Escape, and I'm going to open my scenario. For this workflow, let's look at the PCM MinNet demand week. After I've opened it, let me quickly look at the time duration of the look-ahead. I can see that this scenario has a 24-hour look-ahead. Now, let me execute this scenario. Now that my scenario is complete, let's view some results. Let's start by looking at the dispatch plot. Interestingly, I can see that there is some solar and wind curtailment. Let's look at some of the shadow prices. And let's circle back to that Dighton fuel generator. We can see its maximum active power and the active power that was actually dispatched during the simulation. Finally, let's export the Clearly Flood active power. That's another fuel generator. To do this, I will use the command window. I'm going to produce a table of the fuel generator, and the specific fuel generator I want is Clearly Flood. The property I want is the active power, and I'm going to export these values to a CSV that I'm calling Clearly Flood. Now let's move on to an exercise. Given your coworker just sent you a project that contains the eNet 39 network and a scenario, the PCM peak demand week. Your asks are to add a new demand to the Littleton node called data center. This data center is always on, so the default active power set point is 10 megawatts. It never changes. Execute the PCM peak demand week scenario and determine what is the maximum shadow price at the Littleton node. Pause this video and work on this exercise. Before I work through the solution to this exercise, I'm going to close and reopen Sync to mimic a fresh open. The first thing I'll do is open my network. The next ask was to add a new demand to the Littleton node called data center. Let's find the Littleton node. I'm going to do that by searching in the Model Explorer. Let's find where that Littleton node is on the map. It appears to be in eastern Massachusetts. I can hit Escape to deselect. Let's add a new external to that node. Specifically, I want to add an electric demand. And the name of that electric demand is going to be data center. The next ask says that data center is always on, so its default active power set point is 10 megawatts. A light bulb goes off in my head, and I know that default active power set point is an event property. I find that property, and I can see from the description here that it is the default total active power set point, the psetDef property. From the exercise, I know that I want to set that equal to 10 megawatts. The next ask is to execute the scenario. I can do that by going to the Scenario tab, opening my electric scenario, and from the question, it wants me to analyze the PCM peak demand week scenario. After opening, I'll execute. It looks like my scenario simulated successfully. The final question is, what is the maximum shadow price at that Littleton node? I'll do this two ways. First, using a table. I want to get information about an electric node, specifically Littleton, and I want to get something about the P shadow, the shadow price at that node. I click enter, and now in this table I can sort these shadow prices. It looks like the maximum shadow price is $45.25 per megawatt hour. I could also get that value by using the max function, by evaluating the max, Emax, at my Littleton node, specifically the P shadow. And what I want to make sure is I grab the maximum shadow price at the Littleton node over all of the time steps. And I see that it is $45.25 per megawatt hour, just as I got using the table method above. A final sanity check would be to use the chart window of the Littleton node and visually see that it is 45.25. Thank you for watching the fourth and final video in our Saint 101 video series. We hope that this video series has given you the Saint mindset and the Saint philosophy that you need to do modeling across many domains in Saint. Thank you for watching.